So welcome to my talk. I'm going to talk today a little bit about rough center manifolds. And the idea is that a rough center manifold in some sense is a natural generalization of a deterministic object to the stochastic world. So let me get started. So it's sort of first I have to explain, since this is a stochastic seminar, what is actually a center manifold in the deterministic setting, because I do not expect that if you're coming from a stochastics type background that you know this, but it is a very important reduction tool. And basically you should think these manifolds are things that are happening all around us in the real world in complex systems all the time, whether it's, epidemic outbreaks, climate tipping points. It doesn't really matter. These sort of objects are key for local reductions near transition points in dynamical systems. So you really sort of need to study them. And from a mathematical perspective, we need to sort of also generalize these concepts to stochastic dynamics, simply because we are sort of, we need these extra additional stochastic terms in complex systems to take care of external or internal sort of perturbations that are inherent in the system. And from a sort of pure mathematical perspective, it's just sort of also an interesting curiosity how a dynamical systems theory interplays with rough path theory that's maybe sort of, more well established in stochastic analysis. So what I will do today is I will give you a little bit of background from the sort of ODE world on center manifolds. Then I will do the setup, how to really sort of generalize these concepts to the stochastic world, to the rough path setting. And then I will say a little bit about what are the ingredients in the proof. How do you need to set up a proof for a rough center manifold in the stochastic setting? And I will at least give you a glimpse of what a typical estimate looks like. I mean, I cannot go through the sort of 30 pages of estimates that you have to do, but I at least want to give you a glimpse how such an estimate looks. And then you get a feel, okay, that's probably what I would have to do if I would have to go through all these estimates. Okay. Right. So basic deterministic center manifolds. I will give an example, a concrete one, on the next slide, but I will start with the abstract setting, just that you have seen that this is really quite general. So suppose we have an ordinary differential equation, like an ODE like here, where we have split already near the origin, which I assume to be an equilibrium point. So suppose this point is stationary. So basically the right-hand side evaluates to 0, that I already split off the linear terms. So meaning there's one linear part here, and that will be the center directions, and one linear part here. This will be the stable directions. And what I assume is that the spectrum of this matrix of AC is on the imaginary axis. There could be one eigenvalue, could be multiple eigenvalues on the imaginary axis. And I assume that this spectrum here of the stable part is to the left. So roughly these are all the stable directions. And okay, I could also deal with unstable directions as well that are sort of all on the right-hand side of the imaginary axis, but I won't do that in most of the setting today. You can always think, I can always do a sort of a center stable, unstable splitting, but for simplicity, let us just think about the practical applications case where you have sort of some spectrum on the imaginary axis of this matrix AC and other stuff that's sort of stable. These are all eigenvalues to the left. So, and what is the idea of a center manifold? The idea is, if there's spectrum of this AC on the imaginary axis to leading order, the linear part should evolve sort of more slowly in these UC components than these stable AS components that are associated to S, because somehow the linear part should be dominant. And this means roughly the directions that are associated to the stable directions are fast. They should decay quickly. And the sort of relevant dynamics near the origin should be governed somehow purely by the number of variables that are in the center directions. And what you want is you want to reduce away all these stable directions. And that's natural. It's, like, as I said, in any big complex system, you could think of the climate, if you like, or an epidemic, if you are sort of, looking out in the real world, probably two topics that people are interested in. And suppose there's some sort of instability happening. Well, at some point, the spectrum will be, if you vary a parameter on the imaginary axis, and then you have to get rid of all the other degrees of freedom that are stable. And this is exactly what center manifold theory is doing. It's reducing all these stable directions away. And the sort of geometric idea is you make an ansatz that says, okay, I want to parameterize the stable directions US by the center directions UC by a function or a mapping. And after I have computed this mapping, then effectively my dynamics reduces onto this so-called center manifold. Yeah? So this means you start somewhere, then you get quickly attracted to the center manifold, and the effective dynamics is governed by dynamics on this center manifold. And what you would want is you want that the center manifold somehow is tangent to the linear sort of center directions at the origin, but it could, of course, be a nonlinear object because this FC and this FS, these are truly nonlinear terms. Yeah. So you need to really take care of the nonlinearity. And the idea is, well, you don't know the function h. So what do you do if you're an analyst? Well, you say, well, I need a fixed point problem. So what you do is you try to set up a fixed point problem for h, for this function h. And there are many ways how to set up this fixed point problem. You could also try to use the implicit function theorem if you wanted to. That also works. But you do a sort of classical analytical technique, and people in the 60s, 70s, and 80s worked out all this sort of center manifold theory for ODEs and also iterated time discrete dynamical systems in full detail. Yeah? Very well established. These guys exist under reasonable assumptions on regularity, of course. I need some enough sort of regularity of the FC and the FS. If they're sort of regular enough, then there's a regular enough H that exists. All right, how is this sort of in practice useful? Let me give you sort of a little bit of a sort of example that you would do in a dynamics course. Yeah. So if you haven't, I mean, if you have seen it, it's a bit boring, but let's suppose, you know, you might not have seen it. So you have a two-dimensional example. There's one sort of center direction, 0 times UC. So there's a 0 here, and then there's a purely nonlinear term, UC times US. And there's one stable direction. There's a parameter P, and there's a sort of nonlinearity that's quadratic. The origin is an equilibrium point, and let's say, suppose you wanted to calculate MC, yeah, the center manifold. How do you do this? Yeah, you make an ansatz, so you suppose this function exists, and you suppose at 0 it's 0 because you want the manifold to go through the origin, you want it to be tangent to the origin. And what you do is you implicitly differentiate this guy with respect to time. Then you use the differential equations. That's a little bit of a longer calculation. But if you do that, then in the end, you will find that there is a partial differential equation of first order for H that you will find that you need to solve. And in true fashion of Cauchy-Kovalevskaya type theory in PDEs, you can do this by sort of locally tailoring. So you locally tailor this, you make an ansatz of a local Taylor expansion that you plug into this so-called invariance equation PDE. I did that all for you. And after you did that, you find out that, for example, for this example, the center manifold should be US is equal to P times UC squared plus some higher order terms. Yeah? So there's a computational procedure to get that manifold. And you see this manifold non-trivially depends upon the parameter P, because if P is positive, then the manifold looks like this. If P is negative, the manifold looks like this, and you can plug in that manifold into the actual equation, into the center equation. So you plug in the guy for US here. And if you plug that in, you will find that on the center manifold, there is a cubic equation, and you can show that for P bigger than 0, the origin is actually unstable. And for P less than 0, the origin is actually stable. So this means you sort of use the center manifold reduction to determine when the origin as an equilibrium point is stable for this ODE. And you couldn't decide this purely by linear analysis, so you needed to reduce this. Okay, so this is my 5 to 8-minute spiel on basics of center manifolds. And now the question comes, the natural one, how do you do this for SDs? How do you do this for stochastic systems? And there are people who've tried this, of course. Yeah, there's the long history of, differential equation or stochastic differential equation school of Ludwig Arnold, and people tried this and so on. And one disadvantage always seemed to be that all these invariant manifold constructions relied on certain specific transformations that didn't work for all sorts of SDEs. Yeah, so there was always a restriction. You somehow, you could only treat certain types of noises. You could only treat certain kinds of manifolds. And the idea that I had a couple of years ago was like, okay, why not use the framework of rough path theory? Because rough path theory sort of gives you a definition of your stochastic differential equation in a more classical ODE type pathwise sense. And then use sort of as close as you can the ODE proofs to actually then show the existence of center manifolds. Yeah? And this led to this project with Alexandra Neamtu that we started many years ago. And so here's the setting. I assume I have an SDE. I again assume I've split it into linear and nonlinear part. I assume that there's an equilibrium point at the origin. I also need to assume something more on the B. There's also another condition that I'm hiding here, that there's a derivative condition on the B. So B has to vanish to a certain order. Yeah. So there's another additional condition on B that I'm not showing here. Yeah. And then I want to prove that for this equilibrium point of this SDE, there's again something like a center manifold. And I will introduce what a rough path is, and I will introduce the entire setting, how you can actually go about constructing the correct setup for, getting center manifolds also in the case of an SDE setting. Well, and the upshot is, I will give it away, is well, you can prove that under these conditions plus this additional condition on B, that indeed there's a so-called random center manifold. So you should think of this as a family of manifolds that's path dependent. So basically, if you stick in another path, you sort of get another family of objects. Roughly speaking, you should think this, before we were parameterizing the actual stable directions via the center directions, and now we are parameterizing the stable directions via the center directions and via the noise process. So it's basically now a sort of 2-parameter family of manifolds in some sense, instead of a 1-parameter family of manifolds. Yeah. And this proof avoids completely what was previously used a lot in these center manifold constructions for stochastic equations, so-called Dawes-Sussman transformations, that were sort of able to transform a stochastic differential equation into a random differential equation by a trick. So for example, if you had additive noise here, you could just subtract an Ornstein-Uhlenbeck process. So you write U minus an Ornstein-Uhlenbeck process. Then this SDE becomes a random ordinary differential equation. Then you do all the random ordinary differential equation stuff, and then you transform back and you get a random center manifold. But we wanted to avoid that. And we wanted to also use this as a sort of starting point to introduce rough path theory into dynamical systems more. Rough path theory, very powerful, of course, but mostly existence-based, regularity-based, but not so much dynamics-based yet. But I think this should change. This would be my hope. Okay. How to do this? So first of all, rough differential equations, again, a little spiel of what you need to do. So formally, it's nice in dynamical systems often to work with sort of an integrated version of the equation. And what you would want to do is you would have sort of want to just integrate it up, and you want to work with this. But if you wanted to work with this, then there's always this deal. How do you deal with the stochastic term, E2 Stratonovich? How do you do this? And rough path gives effectively another way to deal with this integral, you could say. Yeah. That's how you should view it. So what is a rough path? The rough path in some sense is, for example, you should think of W as, for example, a Brownian motion. And it's basically sort of I think of this as always like an enriched Brownian motion, or sort of a non-local Taylor expansion of the stochastic process. Not sure whether, other people in stochastics would think about it this way, but I always like to think in a dynamics viewpoint in terms of local expansions. And this is roughly saying you're not only looking at, for example, a Brownian motion or a fractional Brownian motion, but you also look at sort of higher order, non-local, in-time contribution of that Brownian motion or of that fractional Brownian motion, for example. And we will work with alpha Hölder rough paths. The sort of exponent alpha will be within 1/3 to 1/2, like the 1/2 case would be classical Brownian motion, for example. For the other cases, you could think of fractional Brownian motion as an example, and I will assume that they have certain Hölder regularities. Yeah, you could think of, usually we will use some RD as a target vector space of these paths. These paths will be parameterized over 0, 1. So 0, 1 is here the time interval. Yeah, and there's sort of this imposition, how this W relates to this sort of bold W, that's called Chen's relations. That's roughly saying there's a relation between the process itself and the second order process that's given by a certain algebraic relation. Actually, it comes out of algebra from the 50s, out of a paper of Chen. And you could think of this higher order process after you process that relation, that this is roughly saying that this bold-face W is the integral of W against itself. Well, over time, roughly speaking, that's how you can think of it. And it's sort of a non-local additional information. And it's natural that this should be there, because if you think of, for example, a fractional Brownian motion, it's a time correlated process. And roughly, I always think of this time integral sort of keeps track of that sort of extra correlation structure. If you want to think of it stochastically, you can think of it analytically. It keeps track of higher order regularity, if you wish, but whatever way you prefer, it's an enrichment. With this enrichment, you can now very nicely construct further, additional variants of rough paths. There's this nice book by Peter Fritz and Martin Heira, if you want to learn about this. I think there's also a new version out now. It was published last year. And there's sort of another concept that you can build upon a rough path that says a rough path is controlled by another rough path. So you think of W, for example, as Brownian motion, and Y as any sort of rough path. If there exists the Y prime, so again, we will think of this like a derivative, such that you can expand locally at a point, Ys, this this rough path that's controlled by W with respect to the sort of increments of W, and there's a coefficient which we will later on call the Gubinelli derivative up to a remainder. So roughly speaking, a rough path is Y is controlled by W if you can sort of locally Taylor expand it in the expansion functions prescribed by W. And this actually got me thinking after I learned about this, that this must be extremely useful for dynamical systems, simply because it's very akin to something that I'm very used to, which is classical singularity theory or bifurcation theory, where you sort of Taylor expand everything and you're locally working with jet spaces. And this feels like sort of the non-local variant of jet spaces in the stochastic setting. Yeah? So that's why I got interested in this. I thought this is a good idea. Yeah? Okay, you have to show that this remainder has a certain regularity. It's like in Taylor, you show that the next term has the right order. Nothing else. Yeah, it's really looks fancy, but after all, if you comprehend it in terms of jet spaces and Taylor, it's less fancy than it looks at first sight. A few remarks. We will denote by D2R for W the space of controlled rough paths, so all the guys that are controlled by W. There's a semi-norm, that you can define that's basically measuring the rough path. You can also make this into a norm if you put in the right initial condition and so on. But roughly speaking, there are sufficiently nice semi-norms or norms on this space of rough path, okay, of these sort of path spaces. And Y prime I will call the Gubinelli derivative, and I will also say, okay, there are many examples where you can compute the Gubinelli derivative, right? Where you can just sort of say Y is, for example, B of U, and Y prime is actually just some sort of classical chain rule. Yeah. So quite often when we do all our calculations below, really working with Y prime is a little bit like working with a derivative. Okay, just that's sort of the idea. And there's many tensor identifications. I always put myself a reminder. Quite often in rough paths, you're starting to identify spaces of certain tensors with certain RDs or RNs of the right dimension. And the notation is often like the biggest headache. Like conceptually, it's clear what's going on, but actually getting the notation right and getting all the tensor identifications right can be harder than actually comprehending what's going on. Okay, good. So there's a theorem now that says if you have a controlled rough path, so in this controlled space, and you take a partition of 0, 1, then indeed you can define this integral that you need to define a solution in terms of, sort of this theory of Gubinelli of controlled rough path, where roughly speaking, you don't only take the sort of normal increments, meaning the normal increments you're used to from the Riemann integral or the Riemann-Stieltjes integral, but you add to this a correction term. And this correction term is governed by the Gubinelli derivative and the higher order correction that comes with the rough path. And then you can show, if this partition goes to 0, that indeed this is a convergent integral. Yeah. So you can actually show that this stochastic term that we wanted to define, like this last guy, you can define it if W is a rough path by just taking these sort of sums, if you have actually the argument being controlled, which is nice. And this means you can define a solution concept. You can say, okay, the solution of my rough, or well, if it would be a Brownian motion or a fractional Brownian motion, for example, my stochastic differential equation is defined by this formula, because you have made sense via controlled rough path theory of this integral. Okay, so that's my 5 to 8 minute spiel of basic rough path theory, how we need it and how we set it up in our context. So we're working with controlled rough path, and we are wanting a solution concept that's roughly like this. Well, not quite like this, because what we also need is we want to upgrade a little bit. We want to also put the semi-group from the linear part for various dynamical systems reasons. We want to put this into the solution. So we want to move more towards a mild solution type concept where you have a convolution with the linear part that comes in as well. And roughly speaking, what you can show is this is fine. You can still define everything, and you can still go about this quite easily in finite dimensions. In infinite dimensions, it's harder. If S of t would be a semi-group in infinite dimensions, there's all sorts of continuity issues at 0 and so on. And you need to work quite a bit to make this formulation work. But in finite dimensions, this is fine. And you can actually find a nice solution concept. And you can actually do that. And even better, after you have done that solution concept, you can start doing sort of estimates. So here's a typical type of estimates that you can get. So suppose you have a controlled rough path, then you can actually show that this pair, which is basically saying I take the sort of stochastic convolution, I sort of apply this semi-group to the given element of the rough path, and I put the second component also that comes from this controlled rough path, then again, this is again a rough path. Yeah. So roughly speaking, there's algebraic working tools, meaning if you start with a rough path, you sort of start integrating these things and playing with them in a dynamical system setting. You need to make sure that all the objects in your solution again are in your space. This is necessary because remember, in the end, we want to set up fixed point problems. And the first part of every fixed point problem is, here's the first glimpse at the proof, that you need to show that whenever you apply an operator, you again end up in the same space. Otherwise, it makes no sense to set up a fixed point problem. And this is actually possible if you set that up correctly. Yeah? And you need some sort of classical semi-group estimates. This is pretty straightforward in the sense that, you maybe have seen this, and in finite dimensions, this is actually pretty easy to prove. You just write down the matrix exponential and you prove that. Yeah? But you also need certain rough path estimates that roughly say, okay, if you are in a certain alpha-Hölder space, meaning roughly the local fluctuations of this rough path have a certain regularity, then you can bound this by all the data that the input rough path is giving you and by the guy that's controlling it. So roughly speaking, you have something on the left. This will be common in the proof of the rough center manifolds. You estimate this by a certain norm, and on the right, you want data that you can control, right? Meaning the input stuff that you know the norm of and the alpha-Hölder norm of your process. You want the initial datum potentially, you can control that. And you can control sort of the object itself, hopefully, because that's usually in the end what gets controlled by the fixed point problem. Yeah. On the left-hand side, there should be somehow something. On the right-hand side, there should be something, should be the same object, and it should map within the space. So here are the first glimpses of why you could hope that a rough path proof for a center manifold could work. Good. Right. So third ingredient. So as you see in my talk is a little bit, I combine different techniques from different areas. I like this. I know maybe not everybody likes this. I personally like this. So I do it because I think it's cool. Yeah. So that's the third ingredient that I need. The third ingredient is random dynamical systems theory in the classical sense of Arnold. So if you haven't seen it, it might be a bit confusing at first, but you should think of this, roughly speaking, as a stochastic variant or random variant of classical flows for ODEs. Yeah, a flow for an ODE, okay, that's lecture 2 of ordinary differential equations or something in undergraduate. And this is sort of the random version of it. So let's start with a probability space. Assume that there is actually a family of nice transformations. This will be sort of the base sort of metric dynamical system that's roughly shifting around the noise. So you'd think of this theta t always as sort of like a shift. Yeah? It's basically just in space shifting around the noise like you want to have it. Yeah? In the beginning, it shouldn't do anything, and then it should have the typical flow type property of shifting around up to s, and then shifting to t is the same as shifting to t plus s. So translations obviously satisfy this, right? Because translations are trivially satisfying all these properties. That's what we call a metric dynamical system. For example, as I said, you can endow sort of Brownian, the path space, the Wiener space of Brownian paths with this. You can say, take the standard translation space and take Brownian path and shift them around. Then the translation on this Wiener space is actually a metric dynamical system. And even furthermore, you can also extend this to rough paths by just extending the normal shift that you would apply to a Brownian motion. You extend this to sort of upgraded shift that also works in this sort of setting when you have this higher order bold W. And why, how do you guess that this is the right formula? I mean, it's a definition. So, well, you basically go back to rough path theory and you sort of have this analogy in mind that this is roughly think that this is this integral. And then you check, okay, what do I need to make sure of in this integral that if I start shifting, that it's the right integral afterwards? Well, then you come out that indeed, this is the correct definition, how the shift should be defined on the higher order term. So it's a purely algebraic relation. So roughly what this metric dynamical system is doing is just shifting our noise in time to the right place. And it's doing so also on the level of rough path. Yeah? For example, shifting a Brownian motion or a fractional Brownian motion. Good. So now what's a random dynamical system? So a random dynamical system over a given metric dynamical system is basically just a mapping that looks a little bit like a flow. So you have a time, yeah, then you have the randomness, and then you have your phase space, and all this is doing is it's taking basically a starting initial condition and the noise, and it's producing after time t a value in your phase space, starting from x. Yeah? And at the beginning, like a normal flow, it's the identity. So if you start with initial condition, time is 0, you don't flow anywhere. Then there is this sort of more funny property, which is the co-cycle property. It's not the normal semi-group property of a flow. So where you would expect that it's just sort of t plus tau is this first shifting with tau and then shifting with t. It is indeed first shifting with tau and then shifting with t, but the middle term here is important, meaning there's also the noise that you have to adjust for. Meaning after you shifted or after you moved your dynamical system forward at time tau, you also have to adjust the noise, and then you can do sort of the next operation. Yeah? So roughly speaking, on path space, this is sort of adjusting for the problem of having a non-autonomous dynamical system that's forced by a stochastic process. Yeah? Yeah? Good. And it's continuous and measurable and everything. Yeah, like you would to have it normally. That's normal properties of such an operator. Okay, and you can prove that indeed this formula, this mild solution formula that we have for our rough differential equation, this indeed actually generates a random dynamical system. Huh? So you can show that, this sort of operator that's just solving the rough differential equation, that this gives you a nice random dynamical system, satisfies the co-cycle property, has sufficient regularity in the right spaces, and all this sort of stuff. Right, and why do I need all that? Well, I need to define what in the random setting an invariant manifold should be. And for that, I need to sort of this flow definition, because the invariance comes from applying normally a flow operator. And here now it comes from applying the sort of phi operator from the random dynamical system. All right. So here's the definition. So I have the same setting that I have before. Yeah, this is again, the typical setting that I want. Again, there's an additional condition on B. Yeah, and it's a center. I can also assume that there's unstable stuff, but I suppress the unstable stuff. So the linear part splits into a stable component, spectrum on the left, the center component, spectrum on the imaginary axis. There are projection operators onto the center component, onto the stable component, and this is my entire space. And locally at 0, 0, this splits into the entire space. Fine. So what's now an invariant manifold? It's now a family of sets, simply because it's parameterized also by the path that are sort of the input to your stochastic or rough dynamical system. So it's invariant with respect to this random dynamical systems operator. Well, if that's the normal invariance definition you want, meaning the manifold's invariant, meaning trajectories stay in it when you start in it. If you apply something that, this means the initial condition is in the manifold, you put in some noise, you put in some time, and then you want to end up back in the manifold again. But you're not ending back up in that very same manifold generically. You're ending up in a noise shifted version. So this is why I need the sort of translation. This means the manifold is invariant in the sort of non-autonomous sense that you start in it. And for an ODE setting, you would just remain in it. Yeah, as we have seen for our kindergarten example on the second or third slide. But for this random setting, you need to sort of shift that manifold around. And this is what this sort of theta operator does. And then the definition of a rough center manifold is just the very same for a normal ODE center manifold. Well, it's a manifold that's parameterized over the center directions, and it parameterizes the stable directions. Yeah, it's actually an object from center to stable. It vanishes at the origin, and it's tangent to the center space at 0, like this example that we had. So it's the very same definition, almost verbatim, just set up in such a way that the random dynamical system stuff takes care of being able to define the same object. Fine, but now how to prove that existence of that guy HC? Yeah, how do you do that? So now this is a little bit more technical, I have to admit that. So I will try to explain, but this is where the long calculation comes. But I will explain for 1 or 2 slides only why this can work. Okay, how do you construct such an HT? I mean, all the definitions are fine, but how do you construct it? So what's the idea? So the idea is this formula, if you haven't seen it, it doesn't mean much to you. I will try to explain. So there are three different ways that are generically used to prove the existence of invariant manifolds in dynamical systems. One is sort of what we have been using here, the so-called Lyapunov-Perron functional iteration method. What this is doing is you're trying to define a sort of more algebraic type structured equation that is a fixed point problem that you can solve abstractly in a function space, and it spits out after you solve it the invariant manifold. The second technique is the so-called graph transform. What this is doing is it's roughly locally parameterizing everything in a differential geometry way as graphs, and then it's working with sort of local Lipschitz graphs and how they are mapped sort of into other local Lipschitz graphs by the flow. We also believe that if you wanted to do the graph transform method, I think it's still fine. So I don't think there's a considerable difference, but we chose Lyapunov-Perron because somehow it seemed to fit easier with rough paths, but I'm pretty sure graph transform would work too. The third method is implicit function theorem. That's probably a little bit harder to make work, but probably also possible to do, meaning you somehow get the existence of that unknown function from setting up the right implicit function theorem problem in the right sort of abstract function space where you use the implicit function theorem in infinite dimensions to get the right graph. Yeah? It's a method pioneered by Irwin in the 1980s, mid of the 1980s, and there's a nice paper by him. So what we have set up here is a fixed point iteration in Lyapunov-Perron type form in the continuous time setting. And the idea is don't look at the details of these integrals, but roughly the important details are in the times and where the semigroup sits. You see here in the first and the second integral, what you are trying to keep in this sort of J guy is roughly speaking everything that's in forward time in the center direction. So you're keeping the initial data that's starting in the center direction, and you're keeping everything that's sort of in your differential equation definition that is in forward time in center space. And you're trying to get rid of everything that's in the stable space. But how do you get rid of this? Well, you basically go back to infinite backward time. Then you assume your differential equation has evolved for an infinitely long time. And if it did, then of course the stable direction would have damped out because it's the stable direction. So roughly speaking, this sort of formulation, if you look at a fixed point problem in the end, should spit out, after some projection tricks and so on, it should spit out something related to only the center dynamics, right? So this is hard and difficult, but it's the same definition as in the deterministic setting. If I cross out this dW and this dW, you will find that definition in a standard textbook on Lyapunov-Perron methods for ODEs or PDEs, okay? So that's why this definition is natural. You just augment it by the sort of, rough convolution type integrals. Yeah? There's a little bit of a problem with this though, unfortunately. And the problem is this: you need to somehow discretize everything because you're only having most of the rough path estimates. That's a technical point for the experts in rough path. Many of the standard estimates are sort of written out on a scaled variant of 0, 1. Yes, you can stretch and scale and everything, but we in the end decided, okay, we time discretize, and that makes it easier to just get in some of the standard rough path estimates that you can find in Fritz and Hiram. Maybe there's an easier way to set this up. I'm not claiming that, but we did a time discretization and it makes it sort of easier to set it up. Huh? Not claiming that that's the only way, of course. Yeah? Be very aware of that. Then what you need to do, that's another really tricky thing. In deterministic analysis, what you do is, if you're working in the neighborhood of the origin, you're basically applying a cutoff to your nonlinearities to make the nonlinearities locally Lipschitz. You can always do this analytically, of course, because if you have a sufficiently regular function, there are local cutoff functions that make it locally Lipschitz. But now there's a subtlety here, namely the cutoffs have to depend in some sense in a random way on the input path as well. So you have to be careful that many of the cutoff constants and many of the things that you are dealing with also depend upon the input of the rough path. Yeah? That's also quite important. Let me check my time. Very good. I want to finish in roughly 45 minutes, and I think I will manage, which is nice. So you apply cutoff techniques, but you have to take care of the randomness, roughly speaking, in the cutoff techniques. Yeah? Otherwise, you need to make sure that all the constants are tame enough, despite the fact that they are random. But if you're in stochastic analysis, that's not uncommon, right? You're trying to show, for example, that something is tempered enough. Well, you need to take care of the fact that that constant is sufficiently tempered if the input is some process that can fluctuate wildly. Yeah, I mean, nothing that should surprise you, hopefully. Yeah, and you need to define a good function space in which to do the iteration. Roughly speaking, as some sort of scaled or Hölder type variant of bounded continuous functions on the space of rough paths. I will define it on the next slide, but it's ugly. Maybe there's an easier way, don't know. Yeah, but it works. So, and then you do a contraction mapping. That's the hard part. You show that this mapping is indeed a contraction, and you can show that the fixed point after you projected it via the stable projector indeed gives you the center mapping. So this construction, this last step, is very common in deterministic systems. Roughly speaking, you're getting something that has the right flow property, and all you're doing is, in the end, you're projecting away the coordinates that you don't need, and then you parameterize indeed correctly via the center manifold. Yeah, so this looks strange, but it is a standard step in deterministic ODEs already. Nothing new here, right? This is, you can look this up more or less in many books, yeah, on Lyapunov.Perron. All right, let me at least spend 1 or 2 minutes on this function spaces. Although it's technical, I want to at least define it, and I want to show you how one typical estimate in this last step, where you do the contraction mapping estimates, how one typical estimate would look, that you get a feel what the technical work is. So we look at this sort of sequences of discretized rough paths that are time discretized effectively, so that we can hop on these 0-1 intervals. And the space that we are basically looking at is a typical rough path space, meaning this is a normal rough path space like I've defined before on 0-1 with regularity to alpha, but we are weighting it exponentially. This is often nice for certain calculations because you can put in an exponential weight, and quite often that helps. Yeah. Fine, so this is the space in which we are doing the fixed point iteration, and a typical part, and I'm only showing you the deterministic part because the stochastic one is like this. It's like, I tried to fit it on one slide and I was like, yeah, what's the point? I mean, you can't grasp such a big formula in 20 seconds, yeah? Let's at least look at the deterministic part. So this is purely deterministic. This sort of part of this rough path has zero sort of noisy part, and you just want to estimate that if you take two different controlled rough paths, that in a certain formula where you do the sort of actual fixed point iteration, that this is bounded again by the difference between these two guys, because that's how you set up a fixed point problem, right? On the left, you take one guy, say y, you take y tilde, you estimate that after you put it into your fixed point operator on the right-hand side, you get y minus y tilde with a hopefully small constant that's less than 1. And then you apply the Banach fixed point theorem, right? That's how all these fixed point problems are set up. Yeah? And here you can indeed do this. You get a constant that depends upon the semigroup that naturally comes from S. You get a constant that comes from the nonlinearity and its Lipschitz properties. You get a constant that comes from the random cutoff radius, RW. Yeah? And you get actually the differences, or the difference in the suitable rough path topology in this semi-norm. You get, well, in this norm, actually, you can complete that to a norm. You have to put in the initial data, you complete that to a norm. After you completed that to a norm, you actually get on the right-hand side y minus y tilde. And then you do this with all the different terms in this equation. So roughly speaking, you take all these guys, you put in y and y tilde, or u and u tilde, and you're trying to estimate that after estimating all these guys, you end up indeed with something that on the left-hand side has constants that you can estimate that you can make smaller than 1. And then some stuff that just depends upon the difference between the two rough solutions for your fixed point problem. Yeah? So this is how you do that, sort of the actual technical stuff. And well, it's roughly speaking, for every term, you need about 3, 4, 5 pages to estimate it, and every term is done differently. I've shown you a little bit how you treat this F term. And here you need basically for this W terms, you need, for example, estimates that I showed in the beginning. For example, this would be a typical estimate like this, where you actually need rough path estimates to control all the stuff that comes from the random part. Yeah? Okay, it's quite natural, right? We have combined everything. Yeah, we've combined the deterministic stuff with the stochastic stuff to get a fixed point out of our problem. And after you've done that, you finally have the existence of a rough center manifold. So great. Yeah? You get a contraction map, and then the proof is done. But it's long. Yeah? I mean, it's technical. It took us a number of years actually to do this, but okay, I mean, at least now we have a technique that's generic and that hopefully can help us to find invariant manifolds for many other rough differential equations. And indeed, let me put, after we have published this, we have done the rough PDE case. That just appeared on the archive a couple of days ago. So it's quite natural, right? We proved this on the finite dimensional setting. And you think if the method is general, it should also work for rough PDEs, right? You should be able to say, okay, if I have an evolution equation, say a reaction diffusion equation or something else that's nice, and I have a nice noise, and I can define this in the rough PDE setting, I should be able that the same method would work. And indeed it does. So this is the good thing of our method. It's not really specific to the class of equations, as long as there are the three ingredients: a deterministic proof that gives a fixed point with the right sort of techniques, stochastic definition of the random dynamical system, and suitable rough path definitions and rough path estimates. All of this generalizes very naturally. And that's what we were happy about and that I wanted to report about. Future topics, we want to use this in bifurcation theory. As I have hinted at, these center manifolds are extremely important in practical terms. If you have like big jumps or sort of, how to say, bifurcation points that are really crucial for our lives in applications, and we want to apply it to these sort of systems, of course. Yeah, because at bifurcation points, you naturally have spectrum on the imaginary axis if it's a local bifurcation point. We want to make this more computational. That's also very challenging. How do you actually make all these sort of set-valued objects computationally feasible? Yeah, we are working on this. We have a couple of papers forthcoming on this. We have already one where we do it with polynomial chaos, actually, in a joint work with Maxime Bredin. But we are working on that to make it more computational, because this was very abstract, and the practitioners would strongly criticize this by saying, well, if you can compute that manifold, like in my second example, what's the point? Yeah, and they have a point. I fully agree with that point, and we are working and we have tools how to do this. And then I'm hopefully finished. All the stuff is on my website, freely available, and that was 45 minutes. So thank you very much for your attention.
Thank you, Christian. This was a very nice educational